Hey gang, so now we will be further generalizing the n-dimensional Gaussian to any quadratic form, to the general quadratic form, where we have q of x equals x ax plus bx plus c, where, let's say, ab equals the linear algebra operation this. Okay, so x ax equals x transpose ax. Okay, so we will be defining our integral as integral of e to the q minus q of x dx. Okay, and how do we solve this? Let us manipulate this. Let's define some variable x bar equal to minus a to the minus 1b. This is a vector. X bar is distinct from vector. Okay. And q of x bar equals the minimum of q of x. Okay? Now let's plug in and see what q of x bar is equal to. So q of x bar equals x bar ax bar plus b x bar plus c. I'm going to drop the vector signs for convention. C will denote constants. Okay. And so we know x bar equals minus a minus 1b. And so this becomes minus a minus 1b minus x bar as a minus 1 equals I. And remember, a is symmetric. Okay. Minus x plus b minus a minus 1b plus c. And we can actually put this on the other side. Oh, this is not x bar, this is minus b. This is 1/2. 1/2. I forgot to append that to the quadratic form. There we go. Okay. Equals 1/2 b a minus 1b, because since this is symmetric, a minus 1b, b equals b a minus 1 transpose b. A minus 1 transpose equals a minus 1. If a is symmetric, then then a minus 1 is symmetric. Okay, let us continue. And so this becomes plus b minus a minus 1b. So we pull this minus sign out, and we get q of x bar equals minus 1/2 b a minus 1b, which actually equals 1/2 b x bar. Okay, and now let's find the difference. Q of x minus q of x bar will be what's left over, equals some expression. so that we can rewrite q of x as q of x bar plus that expression. And we'll see that this expression is really neat. So let's do that. Our expression is equal to 1/2 x ax plus bx plus c minus 1/2 b x bar minus c. The c's cancel. Equals 1/2 x ax plus bx minus 1/2 bx bar. Okay. What is this? This looks really ugly and not useful at all. Let's substitute minus a minus 1 x bar equals b. Okay? Soft and glow. Okay. It's not minus 1, actually. It's minus a. There you go. Because all we did is x bar equals minus a minus 1b. And we just did multiplied by a on both sides. A minus 1 equals identity. Okay. So this rewrites to 1/2 x ax minus ax bar x minus 1/2 plus, because minus minus, a x bar x bar. So let's just move these to the right for convention, since a is symmetric. Move these to the right. Equals 1/2 x ax minus x bar ax plus 1/2 ax bar minus x. Now we're getting some symmetry. These terms are, ax, did it again. X bar, ax bar. These terms look really similar. So there'll be a similar operation, but this looks different. So I'm gonna do a little trick. Let a constant c bar equal x bar ax bar ax. Okay? And this is just some vector x times a times some vector x. Okay? Which means we know is a constant by linear algebra. Which means if we do c bar transpose, that's going to equal x ax bar. Okay? But since c bar equals constant, c bar transpose equals c bar. Therefore, the inner product x a y equals y a x if a is Hermitian over c and symmetric over r. And so I'm actually going to split this. So I'm going to take this. Equals 1/2 x ax minus 1/2 x ax bar minus 1/2 x bar ax, because these are equal I just split them into 1/2 of the two representations, plus 1/2 x bar. And this looks like terms, and these look like mixed terms. And so our expression ends up becoming x minus x bar a times x minus x bar. If you multiply it out, you get this. Okay, and now we have q of x equals q of x bar plus 1/2 of x minus x bar a. And so this gives us a formula, actually, for the difference, for the value above the minimum. And this is a constant. And this is a function. So if we get our integral e to the minus q of x dx equals integral e to the minus q of x bar plus 1/2 x minus x bar a x minus x bar, which this is also constant along dx. And so that becomes e to the minus q of x bar, since we're not integrating over x bar, e to the 1/2 of u au du, where u equals x minus x bar. And we know what this is because we did it last time. This equals e to the minus q of x bar times root of pi to the n times 1 over det a. And we can actually further generalize this by, if we have the integral, this is generalized Feynman's trick. So if we have the integral of a polynomial of x, e to the minus q of x dx, that is going to equal polynomial of minus partial over partial b, integral dx e to the minus q of x. Because if we see partial b of x ax plus bx plus c equals x. So x basically maps to minus partial over partial b. Okay.